What's going on, folks? We have got a really cool lab, and let's get to start screen sharing before we start talking about anything. I may have gone overboard with the the theory background, but that's my style. I like to make sure everyone understands what the heck we're doing and why we're doing it, why we're seeing what we're seeing. Hide floating mini controls, put my face up there. Okay. So, lots and lots of history. You know what? Before we get started, let's count. One Nobel Prize, two Nobel Prize, three Nobel Prize, four, five, six, seven, eight. So many Nobel Prizes. There's a lot of cool history to this lab, but it touches on an immense amount of things. Um, so, for that reason and many other reasons, this lab, if we were to give it a full treatment, this video would be way longer and it would kind of necessitate the first 2 weeks of an elective course. So I'm going to do my best to make sure that you don't have to understand solid state physics in order to do this lab. So let's get started with just going chronologically, how everything worked. So first things first, probably should have looked up some of these names and how to pronounce them before I got started with this video. Let's see. Röntgen, German, discovered X-rays, basically was shooting electrons in a cathode ray tube. And one thing I forgot to put in this figure was that there was a covering. So he noticed that as he was performing this experiment, there was some radiation that wasn't where he expected it to be. There was like a glow on the side of his lab over there. And he was like, well, that's weird. How about I cover everything? And even with the covering, there was some radiation coming outward. There was like a fluorescent glow on the outside. And so recall from the Frank Hertz intro that we had for the experiments last 2 weeks, that when charged particles decelerate, they emit radiation. So based on this setup, heated filament, heated cathode, electrons are emitted, they fly across because of this accelerating voltage, and then they smack into this anode and they stop. So they were going fast and then they stopped, and so they're going to emit radiation. That radiation is a light wave. And how does one prove that something is a wave? You send it through a diffraction grating. That's kind of the standard method of showing something is a wave. You send it through a slit or you send it through something, and you see if it's constructively interfering. There's an issue here. Um, this radiation, the reason it was called X-rays was because it was unknown. It was based on the, solve for X, unknown variable. And it was penetrating objects. The whole, discovery was based on the fact that it was going through the covering that the experiment was going through. So the very first thing that he did was put his wife's hand up to it and, t take a picture. And well, the whole history of early X-rays was rife with people giving themselves radiation poisoning. Anyway, the issue here is that the wavelength of this radiation has to be incredibly small in order for it to pass through objects, or else it would just knock into the objects and pass through, and it wouldn't coherently go through them. So the diffraction theory, it works best when the wavelength of the object is comparable to the slit or the aperture that it's going through. So this is an issue because, well, in hindsight, we know that X-rays are on like the nanometer scale, and nanotechnology was not around in the 1810s. So how is this going to be possible? How they can't make a diffraction grating in order to see this. There's no way to show that they're waves. And so here's where crystals came in. So one thing that we'll kind of bounce back and forth with is Einstein's four amazing papers in his Annus Mirabilis miraculous year, photoelectric effect, we know that one already. Brownian motion, that's the one we're going to talk about in a minute. Special relativity and mass energy equivalence, those are kind of, equivalent. Special relativity was its own thing, and he used that to derive mass energy equivalence. And we'll jump back to that later. Um, Believe it or not, this is like basically all of these are going to be discussed throughout this intro. So Brownian motion is incredibly complex, and quite frankly, I don't even know if you're going to touch it in StatMech. I don't recall seeing Brownian motion as an undergrad. It was definitely in grad school, but I don't really remember seeing it in undergrad. Just let's show you why. The Brownian motion Wikipedia article. As soon as you get to the theory part of it, yeah, that's why I it's bonkers. It's really, really complicated. Um, the main takeaway, we're not going to discuss anything about what Brownian motion is, but the main takeaway was that it was used, go back here for a second, it was used to prove that atoms and molecules actually exist. And the main result of this, very, very shortly after Einstein developed the theory, was that this guy, Perrin, used it to determine the atom length scale. And that was nanometers or, you know, uh, angstrom scale. So angstroms are 10 to the negative 10. So now this is where we start to say, okay, well, if that at the time that was the smallest known object. And so this guy, von Laue, said, okay, well, what if we shoot the X-rays at a crystal and then the atoms in the crystal will serve as the gaps that we're going to be diffracting with? So this is where he designed an experiment, and it was kind of he showed that diffraction happened, but there wasn't really like a geometric description or explanation of why. So very, very soon after, Bragg and his dad, so this is the first, well, the reason I mentioned father-son duos here is because there's actually another father-son duo later on in this theory background. So what Bragg did, the son, was extending von Lauer's results by showing actually how the diffraction was happening. And it wasn't really that the gap in between the atoms was causing the diffraction. It was actually more so reflection of the electrons bouncing off the atoms themselves. So let's see how this works. So remember that let's first like take a step back and remember from our very first lab, um, what is diffraction or what is the thing that we're observing with diffraction, the bright fringes or the constructive interference. And that occurs when the wave is doing the same thing again, right? The wavelengths match up. So it kind of looks something like this. If you remember that, I didn't want to bring up the PowerPoint slide, I just drew a figure. If one path reaches the detection screen, another path has to be doing the same thing at the detection screen. And so the condition for bright fringes is that the path of the wave is an integer multiple of the wavelength. It has to, constructive interference is when the waves are doing the same thing and they just build on each other instead of destructively interfering. One's going up and one's going down. Those will cancel out. So Bragg diffraction, I'm just going to draw kind of a series of more complicated figures because it's kind of the geometry of this lab is a little bit much. So here's our incoming waves. They're sending, in this case, we're still talking about X-rays. Once we get to our experiment that you can see behind me, it's actually electrons. So a little bit weird, but we're going to start off with X-rays because everything kind of builds sequentially. The early 1900s were a really, really exciting time in physics, and everyone was just learning what someone else did and, extending it. So let's go slowly. This is X-ray waves coming in. One of them is going to miss the top layer. So this is a crystal down here. Crystal is a three-dimensional object. So it's not like going through a slit like we saw in our diffraction grating. It's penetrating an object. And if one of the waves goes through this gap in the atom, but deflects off this atom down here, it will go upwards. So let's think about what is the path difference of these two things. I've drawn these red lines, like kind of like orthogonal here. And the reason I did that was because now this line right here is the same length as this line right here. I probably should have just used a Google image of this instead of drawing my own. And then this path right here is equal to this path right here. So if we compare, let's say this is path one, this is path two, what's the difference in length between those two? Well, it's this shaded red region right here, right? That is equal to that, that is equal to that. So that means the only difference is this extra distance down here. So now we need to figure out how we can actually determine what that length is. So we're going to add some angles, notably like what angle with respect to the crystal does the light hit it at? And also how, what's the distance between the layers of the atoms? And that's actually where we're going to be brushing some solid state physics under the rug later on. So let's add some things here. Okay. So actually, let me, this is like the end result of the figure I drew, but what I did was just, you can see all these little eraser marks here. I just kind of added some things sequentially here. So if the waves hit the crystal at some angle theta, and the distance between the layers of the atoms is labeled by this number d, let me pull up the slideshow. Where did I put that? Bragg slideshow, I think I called it. Slideshow, there we go. Okay, so let me move this over here, and we'll do this view. Okay, so first things first, here's our distance between the atoms. So here's one layer of atoms, here's the other, and there's the distance d. And those are those red lines that I drew from earlier. And the incoming light waves are hitting it at an angle of theta. Next thing we can do is its reflection. This isn't like pure diffraction in the sense that it's going through a gap. It's hitting an atom and coming backwards. So if it's reflection, then the angle on the other side is the same, right? Reflection just kind of it's mirror symmetric. The next thing we can do is start to add some angles, use some geometry. So notice, are there any 90-degree angles I can make use of? That one, right? I mean, the whole purpose of drawing that red line right there to show that these two lines are the same length was to kind of itemize these red segments from before. So if that's a 90-degree angle, I'll just analyze one side. There's no reason to do both. If that's a 90-degree angle, then that is also a 90-degree angle. So now if I analyze this right here, if this is theta, then this is 90 minus theta, right? A right angle is 90 degrees. And so now I can analyze another 90-degree angle, notably this one, the dashed line. So if this is 90 degrees, right? This line right here, let's go back to the beginning. That dashed line and this line that's kind of just bisecting the two paths. So this is kind of like the mirror symmetry axis. Now, if that is 90 degrees, and I've already determined that this segment here is 90 minus theta, that means this one is also theta. Okay, so now I've got a triangle that I can actually work with. So it looks like this. And remember, what was I actually trying to do? I was trying to calculate how long those segments are. So I'm just going to redraw this triangle of interest right here. Theta, d, and this is one of my path lengths, right? It was both of them. So I'm just going to, whatever I calculate this length to be, I'm going to double it, and that's going to be my delta p. So I have an angle. I'm looking for the opposite side to that angle, and this is my hypotenuse. So the opposite side, my delta p, is d and sine theta. And I need to double it because I want both of those red segments. So then I can set those two things equal to each other, just like we did when we were deriving the diffraction grating equation. So we've got delta P is, the wave doing the same thing again, and then delta P based on the geometric interpretation. This is Bragg's law. So this is telling us how things can diffract when it's like reflection about some atom. Okay, so we will get back to this. This is going to be our main equation that we're going to be analyzing. But before we do that, we need to discuss how this was used. So basically, photoelectric effect, covered already, that proved that light was a particle. It was scattering into things and exciting them, and it had, particle nature. This, once they proved that light was actually causing, or the X-rays were causing a diffraction pattern, now they know light is a particle, light is a wave. That's weird. That's the whole point of quantum mechanics. Particles and waves, there's that quantum mechanical duality. So took a little bit, but next decade, de Broglie posed the question, if light exhibits this weird quantum duality, does ordinary matter too? And not all ordinary matter, there's some length scale to it. So what about electrons? Can electrons be viewed as particles and waves? They're pretty small. Do they act in a quantum mechanical way? We probably know the answer, yes, but it wasn't so clear, as you'll see. It took quite some time before people actually accepted this. So some more history here. Here's the other father-son pair, J.J. Thomson. This is the plum pudding guy from when we were talking about the Frank Hertz, and I started that based on like the models of atoms that people were using before Bohr got to the correct one. It wasn't perfectly correct until Schrodinger and Heisenberg got all that stuff later. Um, so J.J. Thomson discovered that electrons were particles. So a little bit of a side note that if de Broglie is right and electrons are waves, that Bohr model that we were talking about with the Frank Hertz background, and that there are orbital, kind of like quantized orbital energy levels for the electrons. If electrons can be viewed as a wave, then that means the orbits can be viewed as like standing waves, right? Standing waves when the wave kind of interferes with itself and kind of goes back. So it would be like should have drawn a figure for this. It would be like nucleus, and the electrons can be viewed as like standing waves that go around itself. So just a little bit of a side note. We'll probably get to that actually when we start talking about the Zeeman effect, because there's more quantization that actually exists with electrons. So just a little side note there. Okay, so now let's kind of take a little bit of a break here. We need to figure out how de Broglie actually made this jump. Like, what equation is he basing all this off? And it goes back to Einstein. So this is where Einstein's kind of mass energy equivalence, the E equals mc squared is the kind of standard thing that you probably remember. Not the full equation. The full equation is not E equals mc squared. It's E squared is kinetic energy plus rest energy. This mc squared, that's rest energy or mass energy. Something can not be moving, like my keys right there have rest energy because they could just spontaneously shoot away. Well, they can't because they're not quantum mechanical. But anyway, so this is the full equation. I'm not going to work through deriving that because then I would be introducing special relativity into this theory background, which is already a ton. If you go to your modern textbook, where this is actually derived is equations 270 and 271. So just leaving that there. There's already so much in here, and that derivation isn't too crazy. If you're comfortable with special relativity. It is kind of crazy. But yeah, I mean, it's Einstein. Let's just trust that Einstein was right. And this is accurate. So energy is made up of kinetic energy and the rest energy of an object. Photons don't have any mass though. So this simplifies a little bit. There is no m here. So now it's just E squared is PC squared. So we can just get rid of the squares, take the square root of both sides, so that we say that the energy of a photon is its momentum times its speed, which is c. Okay, so now let's think about something else that Einstein did, the photoelectric effect. Remember that there was another expression for the energy of a photon. It was based on the frequency that the light was being sent in at. This is just historically something that has always baffled me. This was 1905. It took until 1923 for de Broglie, who was a PhD student when he did this, just to set these two things equal to each other. These are two expressions for the energy of a photon, and no one thought to just set them equal to each other until de Broglie, almost 20 years later. Baffling. So setting these two things equal to each other, we've got PC and Planck's constant and F. Okay, so what is c for a photon? C is speed, so distance over time. And this is, I would say maybe like you can say this is like the photon description or the photon, the particle description. This is the wave description. So what is the speed of a wave? The easiest way to do it is to kind of separate it. Instead of saying velocity is distance over time, you say it's distance times 1 over time because 1 over time is frequency. So now we've got wavelength and frequency. And now we'll plug that in here, and it looks like we're canceling out frequency. So we've got momentum, wavelength, and Planck's constant. And that's all de Broglie did. He said that this is an equation that if an object, right, an object has momentum, mass, and velocity, like an electron. An electron has mass and velocity if it's, being sent at some speed. So his claim was that all objects can be viewed as waves. So in our experiment, what we're going to be doing is, I wonder how easy it is to see. It's not very easy to see. Um, Basically over here, we're emitting electrons over yeah, never mind. It's not very easy to see at all. It's a very complicated structure in there. We are accelerating electrons, kind of, maybe I'll just use this figure. It's quite similar to this. We are emitting electrons, we're applying some voltage to them, and they're charged objects. If they go through a voltage, they will have some energy. So the reason I'm mentioning that is because we can improve on this formula. Not improve, but make it more specific to our situation. So if these electrons have been accelerated through some voltage, just call it V, then the potential energy that they gain, Q and V, is equal to the speed or the kinetic energy that they gain as a result of that. So let's plug in some numbers. Q is E, the charge of an electron. M is ME, the mass of the electron. And so now we can, I should have put a little, I don't know, the cursive thing on this. This is velocity, this is voltage. So now, what is momentum? It's mass and velocity. So we can plug this expression into that expression. So let's plug that in. Yeah, there we go. I did it down here as I realized that that was a little confusing. So I'm plugging in the velocity expression that we get from the energy consideration into de Broglie's wavelength equation. So momentum is mass and velocity. I'm just plugging in the mass of the electron and then doing a little bit of algebra simplification. It looks like I have an ME inside the square root. So what I'm going to do with this term is make it inside of a square root. So then I've got 2 copies of ME up here and 1 copy down here so that it simplifies like that. There's just 1 left over. Okay, so in our experiment, what we're going to be doing is changing the voltage that we accelerate the electrons with and then calculating lambda from Bragg's law. And we're actually going to, I would say, let's leave, if lambda doesn't have a star on it, that's like the theoretical lambda, what de Broglie predicts based on purely theory. And we'll say that lambda with a little star next to it is the lambda that we're going to calculate based on Bragg diffraction. And we'll get back to that in a little bit because with our setup, the Bragg equation is going to get a little bit On one hand, more complicated because we have to do some more derivations, but actually it's going to look easier because we can make small angle approximations and we can use a little bit of geometry to make it easier. So what we're going to do is we are going to change the voltage, independent variable, and we are going to calculate the wavelength based on the Bragg diffraction as a result of that. So voltage, independent, lambda, dependent. So if this is the kind of equation that we're going to try to model this off, let's linearize this to match our experiment. Voltage independent, lambda dependent. So first thing I'm going to do is start to make this look like the equation of a line. The way that I'm going to do that is first get everything underneath the square root. So I'm just going to do the square root of everything. So that means I have to square this h up here, just like I did with this me, so that it looks like this. And then I'm going to take everything, I'm going to get rid of this square, just to make this a little bit easier for myself to calculate. So this tells me that if I, and this is what we're going to do at the very end, we are going to plot lambda squared on the y-axis, and we're going to plot 1 over the voltage that we're using on the x-axis. And so based on de Broglie's equation, those are all constants. Planck's constant, the mass of the electron, and an electron. So if we do this and we plot our Bragg diffraction things, so it's kind of, yeah, I probably should have put the little star there as well. Well, I guess this is just the equation based on the de Broglie equation. But what we're going to do is calculate that, not just assume from the de Broglie equation. We're going to calculate it, and it should be, if we plot lambda squared on the y-axis and 1 over the accelerating voltage on the x-axis, the slope should be this number, if de Broglie was right. Spoiler, he is. So that's just a bunch of constants, and that's something that we can compare our experimental slope to a theoretically predicted slope. So what is this theoretically predicted slope, just to save you a little bit of time? Planck's constant, mass of the electron, all those constants together give us 1.504 10 to the negative 18th. You can check the units if you like. If you were to look at the units of this, meter squared, and then this is 1 over units of volts are joules per coulomb. So joules would be kilograms, meter squared over second squared. So these units would actually work out. Units aren't super important. We're just going to be plotting things and comparing the two values. Okay. So before we get to more discussion of the Bragg diffraction, because that's what we're going to be using, let's discuss what de Broglie was actually trying to do with this, right? He was trying to say that all particles, tiny particles, quantum particles, are waves. So how does one prove something is a wave? Diffraction. So this is where the whole X-ray diffraction of up here um, comes into play, because they were thinking, okay, well, if X-rays diffracted through crystals, maybe electrons can too. Slightly different process. And the history of this is actually kind of weird and interesting. Where'd we go? Down here. Okay. So it's kind of interesting because on one hand, it's interesting for two reasons. It was discovered completely independently by two different people, two different teams rather. Davison and Germer, they discovered it completely accidentally. Something broke in their experiment, and then they discovered this. And the other one was Thomson, who discovered this um, very intentionally. He knew of de Broglie's result and set out to prove it. Whereas Davis and Gemur were doing an experiment, and then they learned about de Broglie and were like, oh my God, it matches perfectly. So very, very different. Davison and Gemur, let's just go chronologically because they were slightly first because they were in industry. They weren't like clued in to academia. They didn't know that de Broglie had even made this, thing. Um, so, basically, what they were doing, it was kind of boring work. They were just firing electrons at samples of, what they wanted to be very, very smooth metal samples and observing the reflection of the electrons off of them. Not super interesting until the vacuum chamber that they housed their sample in broke and it was contaminated with air. And so if the vacuum sample is contaminated with air, the nickel is going to get a bunch of oxygen on it. So it oxidized, and in order to remove that oxygen, they tried heating it up and submerging it in like a basically a stream of hydrogen and trying to rid the nickel of that oxygen. It worked. But what they did as a result of that heating was they annealed the crystal structure until it changed. So basically, what the aluminum, what the nickel looked like originally was like this, very irregular, just all over the place. Like some structures, but completely, there's like domain walls throughout the whole thing. When they heated it, it became a single crystal like this. And that kind of looks like the layers of crystals that we were talking about with the X-ray diffraction. And so when they shine their electrons on it now, the smooth, as basically what they were doing when they were shooting this electron at the nickel, they expected it to just be a smooth intensity as they rotated the sample. They didn't see that. They saw peaks and a diffraction pattern. Where were we? Okay, so they knew about Bragg's diffraction with X-rays, and they were like, okay, there's got to be something similar happening here. And what happened was, again, these were people in industry. They were at Bell Labs, powerhouse of the 20th century. And it was only until Davison, the kind of lead scientist in the team, went to a conference while he was in England and discovered, well, firstly, he learned of de Broglie's theory, and moreover, someone that we'll talk about in with the Zeeman effect and such, Max Born was actually giving a lecture about de Broglie's theory and using Davison's own results from past experiments as claimed confirmation of de Broglie's stuff. And so Davison saw this and was like, "Oh my God, we're behind the curve." So they went back and analyzed their results with de Broglie's theory in mind and found that the wavelengths that they calculated from Bragg's law matched de Broglie's results exactly. And that's what we're going to do. The other team that did this was the next father-son duo in our kind of theory background, conducted a practically identical experiment to Davison and Gemur, but he wasn't doing it by accident. He was an academic. Thompson was I think in Scotland, University of Aberdeen, I think. Anyway, he was in academia, so very clued into de Broglie's work already, and he designed the experiment specifically to prove that de Broglie was right. They both published in 1927, though, so they both, shared the Nobel Prize. Um, Interestingly, yeah, it's kind of cool. This father-son duo, J.J. Thomson, the plum pudding guy, he was the one who discovered electrons, so he showed that they were particles, and his son showed that they were waves with this diffraction stuff. Okay, so enough historical background. Let's actually start talking about our experiment. So remember this angle from the original derivation of Bragg's law. Our experiment is a little bit different. It looks a little bit more like this. We've got our incoming electrons being fired out of our heated filament. The target that we're going to be colliding these things with is kind of like at an angle like this. So that angle, this one, theta up here, is kind of like down here a little bit. And just be aware that these figures that I'm about to be discussing, they are not drawn to scale. It's more so like the target and the screen are that far away, and the diffraction pattern we're going to be showing is very, very small. But I just want to blow these figures up so that we can analyze the geometry a little bit. So if our target is, let's say it's a distance capital D away, So the distance from here to here is d. And the constructive interference that we're going to be seeing on this screen here, we're going to measure that as r. So in this case, our geometry kind of looks like this. This is the beam path coming in, electrons coming in. Here's the angle that these things are, with respect to the beams coming in, with respect to the kind of crystal structure. There's that angle. And remember, this is reflection. So first things first, those two angles are the same, right? Because it's just reflection. That's what reflection is, mirror symmetric. And then let's ignore this angle for a second. Look at this dashed line. That dashed line and the target create an intersecting line. And from geometry, we can pretty much just, well, I could have done an extra 180 minus theta and done some more geometry. Or this one's usually something that people remember from like middle school or something, that if you have two intersecting lines, the angles are the same. So now let's, again, this is not to scale, but now let's analyze this triangle right here. So now this triangle kind of looks like this. In reality, D is massive. So like D is, like that big, and the R's that we're going to measure are like that big. So very, very not to scale. Just wanted to draw it out to make it a little bit easier for us to understand. Basically, I'm trying to say that the angles are going to be very, very small. In this figure, it looks like they're like 60 degrees or 30 or something like that, but they're in reality incredibly small. So the angles that we're going to be working with are very, very small. So what we're going to be doing is trying to figure out that angle, because remember, the Bragg diffraction equation has an angle in it. So let's try to figure out what that is. We're not actually going to be measuring angles. We're going to be measuring distances on the screen. So let's do some small angle approximation. If I have the opposite side of a triangle and the adjacent side of a triangle, I'm going to be using the tan function. And in both cases, for tan and sine, the small angle approximation is just tan of whatever's inside it is equal to what's inside it. So for us, tan theta or tan 2 theta is r, opposite, over adjacent. And we can just get rid of the tan because we're working with small angles. So if theta is small, 2 theta is also small. So this is our equation now. 2 theta is r over d, capital D. So now let's plug this in to the Bragg equation, in which case we are just going to be looking at all the diffractions that we're going to be seeing are just the first one. There's no the screen and the intensity is going to be so dim that we're not going to be able to see anything beyond the first order. So n is just going to be equal to 1 for the entirety of the lab. And again, we're going to use another small angle approximation. So sine theta is just equal to theta, just like the tan one. And so now we can plug in. 2 theta is appearing down in the equation now, and this is based on the geometry of our setup. So now our full Bragg equation is going to look like this. And I'm using this little star to signify that this is not the de Broglie wavelength, it's the Bragg wavelength. So this is our setup. What we're going to do is we are going to, D is fixed. It is written on the top of this, 7 inches. We'll convert that to meters later on. And R is what we're going to be measuring on the screen. D, here's where we're going to be lowercase d. We're going to be brushing some things under the rug here. And as you all know, I don't like doing that. Hence these very, very long videos. I want you to understand the theory of everything that we're doing. I would fume every time as a student I would see the proof is left to the reader. I think that's awful pedagogy. However, determining what D is in our experiment requires a massive amount of solid state physics knowledge. And it's based on the structure of the crystal. So in our apparatus, there's actually 2 different targets, aluminum and graphite. I'll get back to that in a second. But the course in which you would learn the stuff to actually calculate what D is 5,500. It is an elective. I would highly recommend taking it. It is an awesome topic that will get you into really, if you're like me and like, for instance, like my background was in gravity first, and I did, differential geometry, Lie algebras and group theory and stuff, and gravity. And then I realized that all that math is also in condensed matter physics. It's really, really cool. Shameless little plug here. That's my master's thesis. Here's a really cool other, more current set of lecture notes on this topic. It's really, really cool, but it's an elective for a reason. Um, and the topics that we would need to cover in order to fully grasp how to derive what D is for any given crystal, um, they take a long time. Like I took more or less the equivalent of 5,500 in grad school, and it took me at least the first 2 weeks of the course to understand the concepts that we would be needing. If you want some buzzwords to go, look up if you're interested in condensed matter theory, um, reciprocal space, the Bravais lattice, the Miller indices. These are we're going to talk about in just a second. Well, a little bit. Um, it's very, very hard. So I'm going to brush a little bit under the rug here. So even though, like I mentioned earlier, our apparatus actually has two different samples in it that we could potentially be, colliding the electrons with. We are only going to use graphite, not aluminum. And there are a few reasons for that. One, the circular diffraction pattern of aluminum. Let me just show you what that looks like. Oh, come on. iCloud has been so annoying recently. It like doesn't keep things. Anyway, this is what aluminum looks like. It is very hard to measure because this has some distance to it. The like R value that we would be measuring, do I measure from here or do I measure from there? Do I measure in the middle? It's very hard to do the aluminum sample. So that's one reason. The other re and this is, in comparison to the pattern for graphite, which is going to look something like this. Way easier to analyze. Now my R value is pinpoint location to pinpoint location. There's way less ambiguity about what distances I'm measuring with graphite versus or for graphite. So that's one reason. And also it is way easier, and this is a little bit confusing, but because the samples are so close together in that machine, it's very easy to confuse a sample for another sample. Not so much with graphite, though. Graphite is supposed to look like that pinpoint um, hexagon. So let me just show you an example of one of my aluminum, well, what I thought was aluminum, but was not. I could have sworn this was an aluminum diffraction pattern, and I'll zoom in to show you why, right? That looks like a circle, right? If I zoom out, right? Look at the circle out here. That looks more like a, point, 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 point. This is actually aluminum. It's just that my focus wasn't correct and I was maybe slightly touching the graph. It's way easier to confuse aluminum for graphite than it is to confuse graphite for aluminum. So that's one reason, just purely from data taking reasons. And the next reason is because it allows us to brush things under the rug way easier. Um, for aluminum, the Miller indices that we would need to use are quite complicated. So just to give this to you, I hate doing this, but this is just from solid state physics. Um, this is the equation that you would need in order to calculate what little lowercase d is. It is made up of a few different things. A, that one's a little bit easy to understand. That is the distance between the atoms. These are very hard to understand. H, K, and L are called Miller indices. Very briefly, they're kind of like basis vectors for describing how atoms can be arranged among different planes. We don't need to talk about it too much. Now, it turns out that for graphite, that formula reduces dramatically. And the reason for this, um, and it's baffling to me that all the Miller indices for aluminum are listed in the lab report, and yet none of them are for graphite. And it definitely says look at graphite in the lab manual. Anyway, I found something that will allow us to use this. So this is a Army report which talks about hexagonal close packed, which is what graphite is. And if we scroll all the way down to the bottom, this is the diffraction pattern that we're looking at. We are going to be looking at these six first order, right? Not all the rest are like n equals 2, n equals whatever. These are the ones that we're going to be looking at. And so this diffraction pattern correspond again, sorry, this is so much right now, but this corresponds to this zone axis. And the author reports that there are different indices for hexagonal crystal structures, but you can convert them back to the original Miller indices, and they correspond to these ones, right? So C was 0001, right? 0001, and that corresponds to conventional Miller indices H, L, and K of 001. This is another reason why we're just going to use graphite, because what happens to this equation that I'm talking about if this is 0, this is 0, and this is 1? I don't have to worry about all that. Like if we were doing aluminum, we would have to look at all sorts of different combinations because aluminum is kind of, even though graphite is structurally a little complicated because it's hexagonal and it has this weird structure to it, aluminum has weird Miller indices. Graphite is going to be easy. So based on this report, this is telling me that I can just plug in 0, 0, and 1, and the D value that I'm going to be using is just A, the lattice spacing, the distance between the atoms. So I hope that was as palatable as possible. I want to, right, the prerequisite for this course is modern physics, not solid state physics. So this is the equation that we're going to use. This is our final equation. This is the Bragg wavelength. R is what we're measuring, distance from the center peak to all our kind of constructive interferences. D is a constant, 7 inches. We'll convert that to meters. And A is also a constant. That's just something you can Google. And here it is for you. That is the distance between the atoms in graphite. No more solid state physics. We're just going to trust that I've taken solid state physics before. Okay, so here's our equation. This is what we're going to be analyzing. So experimental procedure. Let me plug this thing in before we get started. Don't worry too much about the lab manual makes it seem like you're going to get shocked and killed by this apparatus. It's very similar to the photoelectric effect. It's plug and play. You plug it in, wait for it to warm up, and then turn some dials. Let me just plug this in. It takes a few minutes to warm up. We'll talk through this. Okay. Wait on that. So first things first, as you're waiting, you are going to obviously in your Excel sheet record this number. You're going to need that for your calculations, and then you're going to need the D value, inches, never okay. Convert that to meters. You're dividing that by 39.37. And then the voltages, the ones that I used over here, 6 kilovolts, 7 kilovolts, 8 kilovolts, 9 kilovolts, 10 kilovolts. So those were the ones that worked for me. I couldn't really get anything below 5. I couldn't even see it on the screen. And then what you're going to do is basically play Battleship with these vertical and horizontal. I'll turn the lights off in a second and show you how this works. Um, you can't see the electrons in there. So what you need to do is try to get the electrons to hit the target without being able to see it. So you're just gonna basically sit here and spin these two knobs until you see what well, let me just wait a second until the let's turn the lights off and let's see. Can I raise this up in any capacity? You'll see it enough. Okay, I'm gonna turn the lights off and then we will start looking at this thing. Well, you should be able to see it at least a little bit, just the pinpoint. Let me make this bigger. Stop sharing my screen at least. Yeah, so we're just on step three. Let me stop sharing the screen for a second so that I can see what y'all can see easily. Okay. As close as possible. All right, so I'm going to increase to, yeah, I'm just going to start at 6. I took hours and hours of data to try to get this. The aluminum was so hard to get, and I'm just like, nope, how about we just do graphite? Okay, so I'm at 6. I'm going to turn the intensity up. And be careful with this one. You don't want to burn. You see this line on this? That's from students burning this in the past. So I would say start at like 50%, maybe like 60%. So like, that would be 50. That's 60. Okay, let's see if we can see it at all with the lights off. Again, just Battleship. I'm just randomly twisting these things until I see something on the screen. Yeah, let's turn the lights off. Okay, so believe me, I'm spinning the dials. Okay, I'm going to turn my intensity up to around 75% because that's what I was using when I got data. Yep, there it is. Okay, so now I'm just playing Battleship. I'm just moving my knobs, spinning this thing all over the place until I start to see stuff. Okay, so where'd it go? I basically play Battleship. I just spin it a little bit and I'm getting over there. Okay, didn't see anything. I'm gonna move my other dial. So now I'm gonna basically like make horizontal lines, increase the height, make more horizontal lines. And definitely go slow. Like you want to see the dot first, but then you want to go slow until you hit something. Okay, I'm going to raise it up a little bit. That is a good sign. You see that like, wait, you can't see anything on the screen. Uh, okay, now there's reflection. Once I get the diffraction pattern, I'll show it better. Slowly, slowly, slowly. I'm going to increase the intensity here. There you go. Now you can see it on the screen. Move it over. Just playing Battleship. I was actually getting data like right around here somewhere. Oh, there was something. Oh, so close. We're getting there. Okay, so once I see stuff, I'm gonna very, very slowly move my knobs. Oh, no. That's not too bad. Let me adjust my focus a little bit. It's tricky. Probably isn't worthwhile to put in the video, but is how long it takes. Okay, and then I'm going to start adjusting my focus because I'm seeing some decent hexagonal patterns here. Oh God, it's so hard to see with the computer glare. Anywho, I don't know why I'm even doing this. I should have just showed you the procedure for spinning the dials because I have my own data. I can just show you what it's supposed to look like. We'll probably be cutting a little bit of that. Where were we? Bragg. Not doing aluminum. Here's graphite. Density down, voltage down, and switch off. Okay. So that's what I was seeing, but you couldn't really see it on the screen. And so now we have some measurements to do. We're going to be measuring from there to there, from there to there. Basically, here, let's talk through this. Okay. So in order to measure this stuff, on that screen, I don't see any lines. I don't see a ruler. So what we're going to do, I'm not sharing the screen. Share. There we go. Okay. So where'd my pattern go? There we go. In order to measure this stuff on that screen, I didn't see anything. There were no rulers or units on that screen. So what we're going to do is take pictures with our phone. And our phones also don't have any way to analyze that. So we're going to use a software called Inkscape. And that software is only going to be able to measure the images in terms of pixels. So what we're going to do is hold this caliper. You're just going to spin it until it's at a known distance. I just spun it until it was exactly 10 millimeters. And then next to my diffraction pattern in every single picture, I held that caliper. That one's actually bad. I should hold it so it's easier to measure. Where'd this folder go? How about this one? It's a little bit better. In that case, I would just be measuring from top to bottom. I'll show you how to do that in Inkscape in just a second. So basically what I need this caliper to be next to that diffraction pattern in every single picture so that I can measure this. And then I know how many pixels are, in this case, 10 millimeters. So that's the game plan here. A little bit of a pro tip here. Um, if you're using an iPhone, um, for me anyway, um, my iPhone was set up to, have better storage. So if you go to your settings and then settings, scroll down a little bit to camera and then formats. So let me just show you. Stop share. Oh, this is, come on. What is with Zoom and not being able, this is a Mac with an M2 chip. Camera. Okay, there we go. You're in settings, going down to camera, and then formats. And then this is what I had, high efficiency. You want it to be most compatible. Not a huge deal, but this Inkscape software will not read the you know high efficiency image captures. I don't know. Um, it won't read that. So you'll either have to upload all those files and convert them, or change it in your phone first to JPEGs, and then upload those. Also, another thing, let me show you how to do this as well. Because you're going to need to be taking these pictures in complete darkness, one thing that you can do, again, this is for iPhones. Sorry if you have an Android. Although Android cameras are so much better, you probably won't need to do any of this. One thing that you can do to make these pictures a little bit easier to see, click on this little drop down to be able to, change the settings here, and then go over to exposure and ramp that up all the way. So max exposure, and then where's that other one? Time. No, that's a timer. No, I don't want that. Where is the exposure time? There's usually like another setting, which is like for darkness. Maybe if I put there it is. So if I hold it on the table, this setting will come. It went away. This one. The symbol looks like wow. Okay, there it is. This one. That little setting there, if you drag that all the way to night, max 10 seconds, usually that gave me really good pictures. So max exposure timing is what I've been calling it. I don't actually know what that setting is. Don't know enough about photography. So just a little pro tip, if you are struggling to get some good pictures, need to remember to go back to sharing. Okay, then what you're going to do, I'll show you how to do this in Inkscape. Here's Inkscape. We need to first measure the caliper length, basically so that when we measure the R values, we know how to convert. New document. Okay. Don't need any of this. You can just ignore this page. I have no idea why Inkscape always has this page open. Weird. Going to import and then select your files. Sure, let's see that one. So here's my file. And the first step I need to do before I start measuring any distances here is to figure out how long 10 centimeters is in terms of pixels. So what I'm going to do is I'm going to scroll all the way down on the side here and click on this tool, Measure tool. Then I zoom in as close as I can. And this one's a little bit hard to see. Like, right, that is a circle. So I'm going to try to guess where the edge of the circle is. I got to scroll down and get the edge of the circle. Oops. Something like that. And make it as straight line as possible, kind of line it up with the caliper. So now I know in this image specifically, you have to do this for every single image. Now I know in this image, 10 millimeters is equal to 102.06 pixels. Now that I know that, I can convert my pixel measurements over here, oops, like this. So here's my central beam, and here's all my diffraction and constructive interferences. Go from the center to the center. That R value, 107.76 pixels, I need that in meters. So how am I going to do that? That's what this is for. So then what you can do is say, okay, my scale factor is the length of the caliper that I know, 10 millimeters, divided by the length in pixels that we just showed on Inkscape. Then, when I measure my R in pixels in Inkscape, I can multiply it by that, right? These units are going to cancel, pixels and pixels, and I'll have the radius in meters. Cool. So then what we need to do is just measure a bunch of these. So for instance, you would do one measurement, 106.06 pixels, 108.54 pixels, 104.83 pixels, and so on and so forth. Just get at least four of them, I would say. 106.01. And then take the average of those. So that, oops, didn't mean to show you my data. And then, yeah, so convert those to meters by multiplying by your scale factor. Take the average of all those measurements, and then use that average in your Bragg wavelength formula. So again, A is just the lattice constant. We know what that is. Just Googleable. D, we converted from inches to meters. And R is what we just measured. And then we'll figure out what the wavelength is. And so once you do that for at least four other voltages, so again, I did 6, 7, 8, 9, and 10. So I had five voltages. Then you're going to plot all your wavelength squared, again, because we're doing, where is it? This. We are plotting wavelength squared, wavelength star squared, because we're modeling it after this. Wavelength star squared over wavelength star squared on the y-axis and 1 over the voltage that we're using on the x-axis. And it should be that number, 1.504 10 to the negative 18th. So then figure out what your actual slope is and report a percent error. As usual, this is another plug and play style of lab, so not much error we can do for this. You could, get a range for this value by using Lineast to get an uncertainty in the slope, but percent error is fine because we're comparing the slope value to a theoretical known number from de Broglie. Okay, so Bragg experiment, de Broglie theory. Have fun, y'all.